the previous lectures, we have been talking about work energy theorem, work done by a force, and have defined terms like kinetic energy, potential energy, and so on. However, if you noticed keenly, you would have observed that I have in those lectures avoided talking about defining or talking about a conservative force, or also I have restricted myself to one-dimensional cases. In this lecture, we are going to start dealing with slightly more complicated situations. We are going to go to 3 dimensions and look at what conservative forces are, how we can define them, how we can identify them, and also define potential energy in 3-dimensional cases. Some of the terms and language that I would be using you may be familiar with, particularly the mathematical terms, but in this lecture we are going to put them in the context of work, energy, potential energy, and so on. To start with, let me remind you that when we defined work, and now I am going to generalize to a 3-dimensional case, if I go to from point 1 to point 2 through some path, the work done is defined as an integral F, that is a force that I am applying, dot dl, where the force F is a force applied by me, or if I am considering the work done by the force field, then the force is the force field. Later when we discuss more, we will be focusing on this once more, because this sometimes gets confusing whether it is the work done by the force or work done on the body, work done by us, and so on. In any case, when I define this work, what it means is I am moving a particle in small steps along the path and calculating the work done along each of this segment and adding it up. So I am going to put a sign C here to indicate that I am moving on this curve C. Let me now talk about conservative forces, and if you recall, a conservative force is the one in which no matter what I do, whether I choose this path or this path, or go straight from 1 to 2, or go in some arbitrary way, the work done is always the same. So for conservative forces, work done is independent of the path, and therefore I can safely say that when I am talking about point 1 and point 2, the work done delta W, which is equal to F dot dl along the path C, does not really depend on path C, but only on the endpoints 1 and 2, and therefore I can write this as, let me just use this to define potential energy as minus U2 plus U1. In this case, now let me be explicit, F is the force field, that is the force that is being felt by the body when it is moving. I am not applying for this force. This force is present in the space where the body is moving. For example, it could be the force due to the gravitation of the earth if something is moving around the earth, or if two charges are moving, it could be the force applied by one charge on the other. So now I am being very, very specific. This force is the force given to us, and this U I call the potential energy. This is similar to the definition that I already used once, but now we are trying to go into three-dimensional cases. So, I define for conservative forces, this equals F dot dl, and mind you, I am not going to put any c here because it's independent of the path, and this is going to be minus u2 plus u1, and let me be very specific for conservative forces, and this implies that u2 minus u1 is equal to going from point 1 to point 2 irrespective of the path minus F dot dl, and this is what gives me the interpretation of the potential energy. So, through looking at the work and then identifying that the work done is independent of the path, I define potential energy by this definition. Let me try to understand what it is. So, I am writing, let me again make a figure between point 1 and point 2, that u2 minus u1 is equal to going from point 1 to point 2 minus F dot dl. Imagine I am bringing the body from 1 to 2, holding it in my hand such that I keep it in equilibrium or semi-equilibrium, because I am allowing it to be moved by the force in which it is moving. But I apply sufficient force almost equal to F so that it moves almost in equilibrium. Then minus F is going to be the force applied by us. So, I am bringing this body slowly, applying just enough force so that it does not accelerate, and let it come from point 1 to point 2 in equilibrium. Then this quantity minus F dot dl is going to be the work done by me, because I am holding the body, I am applying a force minus F, alright. So, this is the work done by me. So, by definition then, u2 minus u1 is work done by us or by me in bringing the body from 1 to 2. Let me write it very clearly in the next slide. So, u2 minus u1 is equal to 1 to 2 minus F dot dl. Again, I remind you, I am not writing any C because this is, I am talking about conservative force, and therefore, the work done is independent of the path and it depends only on points 1 and 2, and this then is equal to work done by us in bringing the body or mass m from point 1 to point 2, and again this is true for conservative forces. So, this gives me the definition of potential energy U. It is the work done by us if I bring a body from point 1 to point 2, keeping it in equilibrium with the force field in which the body tends to move. Let us take two examples. Let us take your familiar example of a body moving, say, from point 1 on the surface of the earth to a point 2 which is not very high above the earth, so that I'm going to make the approximation that the force remains roughly the same. So the force applied, or the force field that the body is moving in, or force applied by the earth, is nothing but mg j with a minus sign, because I'm going to take this as my y-axis, this as my x-axis. Only y-axis matters in this case. And when I move the body up, dl is going to be dy j, and therefore u2 minus u1 is going to be minus f dot dl, and therefore mg dy going from 1 to 2, and this is equal to mg y2 minus y1, which is your familiar expression for the potential energy. When we work in terms of vectors, sometimes we get into confusion, and let me just take that as an example. Let me take this as an example to show that. Suppose instead of moving up, I decided to come this way from point 2 to point 1. In that case, again, force F is equal to minus mg j, and you're going to now say, since the body is moving this way, dl is going to be minus dy j, and therefore u, since I'm moving from point 1 to 2, this is going to be u1 minus u2 is equal to minus f dot dl, and that's going to be minus mg j dot dy j integral, and I end up getting minus mg, this is moving from 2 to 1, and therefore I'm going to get this y1 minus y2, which is equal to mg y2 minus y1. Now you notice in the previous slide I had obtained u2 minus u1 as mg y2 minus y1, and now I'm getting u1 minus u2 as mg y2 minus y1. Where is the mistake? And this is where a lot of confusion at times arises. The mistake is here. You see, when I'm taking dl to be minus dy and then again putting limits from 2 to 1, I am actually double counting the minus sign. The proper way to do it would be to write again u1 minus u2 is equal to integral going from 2 to 1 minus f dot dl, and this is going to be equal to, now you see dl is this way, I am moving down, minus f is this way, and therefore minus f dot dl, the angle between them is 180 degrees. The magnitude of minus f is mg, magnitude of dl is dl, with a minus sign in front. That minus sign comes because of cosine of 180 degrees, and I get this integral going from 2 to 1, and now I know magnitude of dl is nothing but minus dy, because y I am measuring going up. Now if you put in everything correctly, you get u1 minus u2 to be equal to mg y1 minus y2, which is negative of u2 minus u1. Correct answer. So you see, you have to be careful in doing this. Always make sure that you are not double counting. Going from one point to the other, the general displacement is dxi plus dyj plus dzk, and that's going to be your dl. The sign is properly taken care of by these limits. Or if you take it explicitly, then you have to be careful as to what is the relationship between dl, the direction of it, and a general displacement vector dr, which is equal to dxi plus dyj plus dzk. In this case, the relationship happens to be with a minus sign in front. As another familiar example, let me take one charge Q1 and let's assume it's fixed somewhere. Let's take the other charge Q2 and move it. Let both the charges be of the same sign so that the force is moving outward, going outwards. Since you know polar coordinates by now, I can write this force on Q2 as K Q1 Q2 over R square along the direction R. I want to calculate the potential energy of Q2 in the field of Q1. So by definition, if I move from point 2 to point 1, this is going to be equal to, say, from R1 to R2, let me move radially, minus F, so that is going to be minus K Q1 Q2 over R square R dot dr R, and that gives me K Q1 Q2 1 over R2 minus 1 over R1. So in the force field of charge Q1, when Q2 moves, U2 minus U1 is going to be equal to K Q1 Q2 1 over R2 minus 1 over R1, where this refers to R1, this refers to R2. Usually what we do is define a point, for example in this case R1 to be infinity, where I take U1 to be 0 as a reference point, and then your U at R becomes K Q1 Q2 over R. Notice again, when I calculated this, I put minus K Q1 Q2 over R square R as the R unit vector as the force, and that is the force applied by us, the external agency, to keep the charge Q2 in equilibrium while moving it. Of course, if R2 is greater than R1, that means 1 over R2 is less than 1 over R1. I am moving the body from inside to outside. This implies U2 minus U1 is negative. The work is being done on the external body, on the body that is keeping the charge in equilibrium when the particle moves, or the charge particle Q2 moves from a point R1 to R2, which is when R2 is greater than R1. You are extracting work. The work is U2 minus U1 is negative. Work done by me is negative. That means the work is being done on me. The force field is doing work on us. And similarly, if R2 is less than R1, in that case U2 minus U1 would come out to be greater than 0, and therefore the work done by us is going to be positive. We are pumping in energy. We are doing work. Work is not being done on us. These are points I am emphasizing because a lot of people get confused on such things as whether the work is being done by us, work is being done on us, and so on. So when I am defining potential energy, if delta U, that is U2 minus U1, is greater than 0, then work is being done, or let me call it positive work is being done by us when delta U, which is U2 minus U1, is less than 0, work is being done on us. Keep this in mind. Having looked at these examples, let us now, still focusing on conservative forces, ask the inverse question: what if u, the potential energy, is given as a function of position of the particle, that is u x y z is given. How is given? How do I calculate the force? Okay. If you like, I call this the inverse problem. Because what I have done so far is defined delta u is as the work done by us in moving a particle from point 1 to point 2. I am now asking, given this, how do I calculate this? Let me remind you what we did in one-dimensional case. In the one-dimensional case, we said that force at any point was minus du dx, where x is the displacement direction. If you recall from the previous lecture, I had in fact made a potential hill something like this and had pointed out how forces are and what are their directions at different points. Now, what do we do in three-dimensional case? We again go back to our basic definition and see if I move from one point x1, y1, z1 to a nearby point. Let me call it x1 plus delta x1, y1 plus delta y1, and z1 plus delta z1. Then the work done, since this is a conservative force field, F is going to be F dot dl. Work done by us is going to be minus F dot dl, and this is going to be delta u. That is the change of u between this point and this point. So, between 2 points I am defining delta u, which is equal to minus F dot delta x1 I plus delta y1 j plus delta z1 k. And therefore, I could write this as minus fx delta x1 minus fy delta y1 minus fz delta z1. Notice this comes out very neatly. It doesn't matter which order I go from point 1 to point 2, because I am talking about conservative force field. I could go from x1, y1, z1 to x1 plus delta x1, y1, z1, go from here to x1 plus delta x1. I am moving particle along the x-axis first, then along the y-axis, and then from there I could go to x1 plus delta x1, y1 plus delta y1, and z1 plus delta z1. And along each path, when I move along the x-axis, I do this much work. When I move along the y-axis, I do this much work. And when I move along the z-axis, I do this much work. If you like, I can call this delta u is equal to change in u when I move along the x-axis, change in u when I move along the y-axis, plus change in u when I move along the z-axis. When I move along the y-axis, there is no work being done against fx. I am moving perpendicular to fx. So, if we move along the x-axis, then delta u y, which is going to be minus f y dy is equal to 0. All the change in u comes only due to this. So, if I keep y and z fixed, I have delta u x, which is equal to f x dx, keeping y and z fixed. No work is done against forces in y or z direction when I move along the x-axis. Let me put a minus sign here because this is a force applied by us. And therefore, let me now define something called the partial derivative, which I will say is delta u over delta x, partial derivative with respect to x when y and z are kept unchanged. And let me call this du dx, and you see then therefore from the definition that delta u, if I move along the x-axis, is going to be minus fx dx, gives me fx as partial derivative with respect to u, and it is understood y, z are constant. So, this is pretty much like one dimension, that I am calculating the derivative of the potential energy. However, since I am talking about a three-dimensional case, I have to be slightly careful. When I am moving along the x-axis, I do not change y and z, because that will unnecessarily mix up things. Similarly, I can now write that since delta u is equal to minus fx delta x minus fy delta y minus fz delta z. So, if I am moving along the x-axis, change in u is only due to the force component along the x direction, and therefore, fx is equal to minus partial derivative of u with respect to x. Similarly, fy, the component of the force along the y direction, is minus du by dy, and force along the z direction is going to be minus, or the component of the force along the z direction is d by dz. By writing this partial derivative, I mean in this case x and y remain constant. I do not change them. I move along the z axis. In this case, I keep x and z constant, and in this case, I keep y and z constant. So, I have introduced a new term called the partial derivative. Physically, what it means is, since I am talking about a conservative field, when I am moving from point 1, this point to this point, I am first moving along, let us call this the x-axis, the y-axis, the z-axis. I move along the x-axis, find out how much is the change in potential energy, and that is going to be only due to the component of the force along the x direction. Then I move along the y-axis, and then I move along the z-axis, and I calculate in each case partially how much is the change in potential energy. When I move along the x-axis, change in potential energy comes only due to the x component of the force, and therefore, it is related to the partial derivative of u with respect to x. When I move along the x-axis, change in potential energy comes only due to the component of the force along the y-axis, and therefore, that is related to the force, the change in u with respect to y, and this is precisely why I get fx equals minus du dx, fy equals minus partial of u with respect to partial of y. And similarly, when I move along the z-axis, the only component of the force that changes the u is the z component, and therefore, this is partial of u with respect to partial of z. So, I have gotten all three components, but remember I am talking about vector quantities. Is there any compact way of writing it? So, I write the force, the net force, which is equal to fx I plus f y j plus f z k, and this comes out to be minus partial of u, partial change derivative of u with respect to x I minus partial derivative of u with respect to y j minus partial derivative of u with respect to z k. And the compact way of writing it is by introducing a new operator called the gradient operator. I am going to write this as minus a vector differential operator acting on u, where I will write this as I partial with respect to x plus j partial with respect to y plus k partial with respect to z. When I write this in front of a potential energy u x y z or any function of x y z, what it means is take partial derivative with respect to x and put I, multiply this by I, take partial derivative with respect to y, multiply by j unit vector, take partial derivative with respect to z, multiplied by k unit vector, and add all three. So, this gives me a vector after taking the partial derivative. This is known as the gradient operator. So, I have introduced a gradient operator. This is like the three-dimensional analog of the one-dimensional differential operator, which I will write as this d by dx plus j, I should write partial, say partial of with respect to y plus k partial derivative with respect to z. Since I am talking about three-dimensional case, this gives me a vector quantity, and the force of which the potential is given as minus the gradient of the potential energy u x y z. Again, if you are feeling a little uncomfortable, go back to one-dimensional case and you will see there I get plus or minus signs in the derivative, and that means either the function is increasing to the right or decreasing to the right depending on the sign. Similarly, this in three-dimensional case gives me in a particular direction if I go how the function u is changing. Remember again, delta u is nothing but f dot delta L or dl, and this is nothing but minus partial of u dot, this is a vector quantity, delta L. So, it really again describes the change in a function u, but in a three-dimensional case depending on which direction I am moving. So, slightly more subtle than the one-dimensional case. We will now try to get some more insights into this, but as far as the definitions are concerned, it is very clear that if I want to get, given a function u x y z, if I want to get the force F, this is going to be equal to minus gradient of u x y z, and its in explicit form is going to be minus I partial of u with respect to x minus j partial of u with respect to y minus k partial of u with respect to z. As a simple example, let us take again a charge q1 and charge q2 at a distance r from it, and we have already seen, and you also know, that ur is given as k q1 q2 over r, and if I want to get the x, y and z components, you take this derivative and you will see that the force F would come out to be correctly as k q1 q2 over r square r. I leave this as an exercise. Having defined the force, having obtained the force from the definition of gradient, which I wrote as minus I partial u partial x partial of u with respect to y minus partial of u with respect to z, I would like to give a word of caution. Since now you are familiar with different coordinate systems, do not directly write gradient in other coordinates. For example, if I take spherical polar coordinates as this, this is not correct. It's not even dimensionally correct, because this should have in the denominator dimension of length. It doesn't even have that. To obtain these things in other coordinate systems, you have to make a proper transformation. For example, in this case, in the spherical polar coordinates, for example, the partial derivative is given as, in direction of r, it is indeed partial with respect to r. On the other hand, in direction of theta, it is like this, and in the direction of phi, it is divided by r sine theta d by d phi. And that makes perfect sense, because this is the distance covered in phi direction, this is the distance covered in theta direction, this is the distance covered in r direction. So just a word of caution that when you go from one coordinate system to the other, take proper transformations to define gradient operator. Let us now try to get some feeling of this, because in one dimension it's quite easy. You've been thinking in terms of one dimension, and you can see that if I go so let's just first say 1D case. The familiar case is if du dx is greater than 0, u increases with x. If du dx is less than 0, u decreases with x. What can we talk about in 3 dimensions? Does it increase in all the directions? How does the gradient give you in which direction is the function changing, and so on. So for that, let me first introduce the concept of constant potential energy surface, or in 2 dimensions what are called contours. And probably when you're doing your geography or something in your 8th or 9th grade, you have come across such term as contours. Now for a constant potential energy surface, I define that surface in 3 dimensions as u, x, y, z, that surface over which this is a constant, or the contour in 2 dimensions is u, x, y is a constant. For example, if I take the case of one charge q2 moving in the force field of this q1, then I know that potential energy u at r is given as k q1 q2 over r, and ur is equal to constant would imply that r is a constant, and therefore in this case the constant potential energy surface is going to be a sphere. As another example, just cooked up example, let me take u, x, y to be equal to some constant k times x, y. And if I am looking at contours, curves over which u is a constant, I should have k x y is equal to c, a constant, and therefore y equals c over kx, which are nothing but different hyperbola depending on the value of c. So these are the contours for this particular function. Now why do I need this? I need this to get a feel for what gradient operator is. So let us take a 3-dimensional case or a 2-dimensional case where I have a contour or a constant potential energy surface, and let me move along this, along the surface. For example, I can move, in the case of say Coulomb potential, if I move along the sphere, then I am keeping u constant. Similarly, in the case of u being equal to kxy, if I move along this hyperbola, u remains a constant. And therefore, if I move along the contours, delta u is 0. But by definition, delta u is also equal to gradient of u times delta L, where delta L is the distance moved. This could be delta L in this case on the sphere in any direction. This would be delta L in this case, this way or this way, doesn't matter. Nonetheless, no matter what I take this to be, delta u comes out to be 0 always if I move along a constant energy surface or a contour. And this implies that the angle between gradient of u and delta L along the constant energy surface of the contour is equal to 90 degrees. All right, and this implies that gradient of u is perpendicular to the constant energy. When I say energy, I mean potential energy. So, let me be explicit, potential energy surface or contour in 2 dimensions. All right. So, first thing we conclude is that the gradient of a function u is going to be perpendicular to its constant surface or the contour. I still have not fixed the direction. Is it going to be towards increasing u or decreasing u? Recall from the one dimensional case that I just mentioned, if du dx is positive, that means if I go in positive x direction, u would be increasing. Can I say similar thing about this? Let us look at that. Then I will take an example and show this again. So, first conclusion is that gradient of u is perpendicular to the constant energy or potential energy surface or contour. Number 2, the question I ask is gradient of u from large u surface to small u surface or the other way? So, let me just picturize this. Suppose I have, let me take 2 dimensional case since this is easy, a contour, and let this be u1, u2, and let u1 be greater than u2. So, I know gradient of u is either in this direction or in this direction. Let me come from surface 1 to surface 2 by delta L. Then I know that u2 minus u1, which is change in u, is going to be equal to gradient of u dot delta L, and this should be less than 0 because I have already taken u1 is greater than u2. This can be less than 0 only if delta u and delta L make an angle of 180 degrees. So, I conclude that delta u should be in the direction opposite to delta L in this case. So, it is pointing away from the direction in which u is decreasing, or it is pointing to the direction in which u is increasing. Let us see that explicitly. If I on the other hand go from u2 to u1, let us write it here, then u1 minus u2 is again going to be gradient of u dot delta L, let me call it delta L2, and this is going to be greater than 0, and that would be the case if delta L2 and delta u are in the same direction. So, it points perpendicular to the constant energy surface of the contours and in the direction of increasing u. So, two things we learn about the gradient. Are number one, perpendicular to constant u surface, number two, points from smaller u surface to larger u surface, or in short, points in increasing u direction. That is the kind of feeling now I develop. I imagine a constant energy surface, and then u gradient of u is going to be perpendicular to that and is going to point in the increasing direction. That is quite understandable if I go back to the one dimensional case also. Recall there that f was equal to minus du dx, so that the force direction, if you recall that example, was towards decreasing u. It was this way here, this way here. This is the force direction. Rather than writing this way, the force was in this direction. Here, this is one dimensional case. In this case, it was in this direction, because du dx is positive, force is in negative direction. So, it was in the direction of decreasing u. So, in 1D case, f was in decreasing u direction. How about the 3D case? In this case, I have force which is equal to minus the gradient of u, and gradient of u is in increasing u direction. So, force which is minus gradient of u is in decreasing u direction, and it is perpendicular to constant u surface. So, this sort of gives you a feel for this, and this is absolutely consistent with what we learned in one dimensional case. Let us take an example. The simplest again being force between two charges. As I said earlier, the constant energy surface is a sphere. U is k q1 q2 over r. If charge q1 is here, then force I know on q2 is going to be radially out, and you also know that potential energy goes down as I go farther and farther away. And also, since this is radially out, it is always perpendicular to the constant energy surface. You should work out more examples like this to get a feel for the gradient. Let us take another example. Let me just hook up u xy to be k xy, as I said earlier, as an example that I took earlier, and let me now plot the constant u surfaces. These, as I said earlier, are going to be hyperbolas depending on what C is, and so on. Now, since u xy over these surfaces is a constant. This implies that this equals k xy equals c, u xy equals k xy equals c, and that means along the constant energy surface, let me take one particular one of them, y is equal to c over kx. If I make a displacement along the constant contour surface or along the constant energy surface or the contour, I am going to have delta L, which is equal to delta x along I plus delta y along j. But because of this relationship, delta y is going to be, delta x I remains, delta y is going to be c over kx square with a minus sign delta x j. So that if I move along the contour, delta L is going to be I minus c over k x square j delta x at a given point x. So remember this is I minus c over kx square j delta x. So delta L is I minus c over kx square j delta x. U is equal to k x y, and therefore gradient of u is going to be ky along I direction. When I take partial derivative of this, I keep y constant and differentiate with respect to x, plus j k x. And since this is a constant, I again can write on that particular curve I k y is nothing but c over kx plus j kx. So at a given point on that curve or the contour, gradient of u is going to be I c over x plus j kx. And you can see if I take the dot product of delta L and gradient of u is going to be 0. I get c over x minus c over x, which is 0 at all the points, and that shows you that delta u is perpendicular to delta L. Let me show it much more explicitly. So I got delta L, which was equal to I minus c over kx square j delta x at a given point, and gradient of u, which was equal to c over x I plus, let me just see what it was, plus kx j kx, so that gradient of u dot delta L is 0, and therefore gradient of u at any point is going to be perpendicular to that surface, and the direction is going to be in the increasing direction. You can see from here, for positive x and for x on the positive side, it's going to be like this. You can also confirm for yourself, as c increases, the contours become like this, so that u, the gradient of u is really pointing in this direction. That I hope by now gives you some feeling for the gradient operator. You could also try it on the negative side. On that side, the gradient of u is going to be perpendicular but pointing in this direction, because again increasing c means I am going farther and farther away on these contours. So far we have talked about conservative forces and how in a conservative force the force and the potential energy are related. I have shown you that the potential energy, when I take its gradient, gives me the force. The force is in the direction perpendicular to the constant potential energy surfaces and in the direction of decreasing potential energy. In the next lecture, we will take one more example of calculating the force from the potential energy using gradient and also talk about non-conservative forces.